Hello students, welcome to Inside Physics. Today we are going to discuss about Kepler's laws, a very famous laws regarding our planetary motion. So, if you go into a brief history of the planetary models that have come across uh, previously, it was the Ptolemy who was announced a geocentric model 2000 years back. So, that was the first model where the planets are actually assumed to be revolving around the Earth. So it was proved wrong by Copernicus later, after maybe after some 400 years later. So Copernicus, in his heliocentric model, he told that all the planets are revolving around the sun. The sun is at the central, and the planets are revolving in an circular orbits. So this is what the Copernicus told, and later the circular orbits concept was denied by the scientists who come across after the periods of Copernicus, these Kepler and Newton, and later the Tycho Brahe, who was a scientist who observed the planetary movements throughout his life with his naked eye and noted some observations as a data. So this Kepler is a assistant for Tycho Brahe, and he actually taken the data from his master, and he analyzed the data and proposed three excellent laws which are called Kepler's laws of planetary motion, who actually recognized by all across the world, and they are proved to be very right considering the planetary motion. So he lived around 1570 to 1640, Kepler, the era of Kepler. So he proposed three interesting laws. So before going to the Kepler's laws, we need to know the model of a solar system. Now it is, we all know that the planets are revolving around the sun in an elliptical orbits. It was not like that proposed by Copernicus, as if they are revolving in circular orbits. It was proved to be wrong, and now we know that these planets are revolving in elliptical orbits. So coming to the Kepler's laws, what is the first law? Law of orbits. Law of orbits. So we all know this law is actually saying that every planet revolves in an elliptical orbit around the sun, having the sun at one of its foci. So we all know ellipse has two foci. I already given a small video on this, how to draw an ellipse. So here, if you consider the ellipse, and this is the major axis passing through two foci, F1, F2 are considered to be two foci of this ellipse. If the sun is actually at one of its foci, that is what this statement of law of orbit says. Every planet revolves around the sun in an elliptical path, having the sun at one of its foci. The sun may be here or here. These are all, this is focus 1, this is focus 2, and we call them as two foci. The sun is here and the planet is revolving like this. Okay, so this point, the nearest point from the sun to the planet, is called perihelion. Perihelion. This is denoted by P, and the farthest point from the sun is called aphelion. Okay, So this planet is revolving around this sun in an elliptical path. That's what the law of orbits says. So this is major axis, and if you take the center of the ellipse as O, and this is called OP, is called semi major axis, and this is also, if you take it as A, OA, aphelion, this is perihelion, and the distance OA is and OP are called OA or OP, or is called semi major axis. And the line drawn perpendicular to this major axis, this line is called minor axis. This is about the first law. Now we'll see the second law, which is about law of areas. Law of areas. So what is the area? We are talking about which area here? The second Kepler's law. Law of areas. Now here, if you are trying to understand what is an area here, it is the area covered by the line joining from the sun to the planet. The line joining from the sun to the planet actually sweeps an area in equal areas in equal intervals of time. So we see what is that in a clear explanation. See here, I will draw an ellipse again. Okay, so here see, again we will need to draw the semi major axis. This is the ellipse. We need to draw the semi major axis, and you say the planet is here, say it is earth, and we know the sun is anywhere at 2 foci. It may be here or here. We'll take the sun here, and the line joining the sun to the planet. So this is the line joining the sun to the planet earth here. This line sweeps equal areas in equal intervals of time. So this is the line, and the earth moved from here to here. So this is a point P, and the earth moved to a point P dash. Okay, and the velocity of the earth is V. It will change, the velocity will change according to the position of the earth. So if it is far away from the sun, the velocity, the speed of the earth is slow, and when it is nearer to the sun, the speed of the earth will increase because of, to conserve the angular momentum. So here the velocity, the speed is v, and it is moving from a point P to P dash. Now again the line drawn to the planet is P dash. So the area covered by this line joining the sun and the planet is this. So if this is the area covered, say in time t, and if you take this the same planet earth from moved from here to here, moved from here to here, that means here the line joining is this, and also the line joining is this area is covered by the line joining the two planets, sun and earth. So this is the area covered in the time t. So if you consider the time interval here, is same time interval t, and here also the same time interval t. In the same time intervals, the area covered by this line is same. That means it sweeps equal areas in equal intervals of time. So how this as assumed? How do we know? These are all the distances are very large between the planets and the sun. How we actually come to know these areas swept in equal time or same? Have you gone to the space and with some scale or something to measure these distances? And how we assume means, see, we assume these physics principles based on the observations. So we all know that the farthest planet like Neptune or Saturn, they move slowly. They have a time period more than 1 year. The time period is very high for them. That means they are moving very slowly when they are far away from the sun. So the closest planet like Mercury will be moving faster. So by these observations, we have the Kepler has taken this assumption, and it has proved to be very right and converted into law of areas. So this is about the second law. And what about third law? Kepler's third law. So the law says a relation between the time period of a planet and the semi-major axis. What it says? The third law, law of periods. That means time period. Law of time periods. So what is this law says? Time period here is always denoted by capital T. What is the time period of a planet? The time taken for a planet to revolve around the sun one time. So for Earth it is 1 year, we all know. So what this law says is the square of the time period of a planet is directly proportional to cube of the semi-major axis, where A here is semi-major axis. A is semi-major axis. Okay. So by this we can say t square by a cube must be a constant. Okay, t square by a cube, this is called the quotient. This is called the quotient denoted by q. This will be around 3, nearly around 3 for every planet. That means if you divide the square of a time period of a planet with the distance, the semi major axis distance of the planet and the sun, and the ratio t square by a cube gives a constant which is called a quotient, that is nearly 3. So what these time periods are measured in years. The distance of this semi-major axis is measured in the units 10 to the power of 10 meters. Okay, so this is how the law of time periods is understood. So there is a concept of central force. We all know the gravitational force is a central force. Central force is actually conserves having a characteristic of law of conservation of angular momentum. In case of a central force, law of conservation of angular momentum is obeyed. So if here the gravitational force is a central force, that means the line joining it, the central force acts along the vector joining the sun and the planet. So here we see what is the area swept in a particular time interval, and we derive a small relation between the angular momentum and the area swept. So by law of conservation of momentum, we can say that the angular momentum is conserved. So the area swept out delta A can be written as half into r bar cross v bar delta t, where r is the distance and v is the velocity speed of the planet, delta t is the time interval. Okay, when this, if you want the area covered in a particular time interval, we can write this as half into r bar cross v bar, right? So I will multiply this, the right hand side terms, with mass, numerator and denominator are multiplied by mass. So here what I can write, half into r bar cross v bar m by m. So we know that the linear momentum p is equal to mv, right? Here what we can write, half into r bar cross p bar by m. So delta A by delta T, the area swept out by the line joining the sun to the planet in a time interval delta T is given by this one, and this finally can be written as half into, see, the this position vector into linear momentum. That means this can be considered as a distance between the planet and the sun, and the linear momentum, their cross product will give the angular momentum by mass. So what we got finally, delta A by delta T is equal to L bar by 2m. So this is how we can understand the areas swept out by the line joining to the sun and the planet. This is all done based on the observation of law of conservation of angular momentum, because the gravitational force is a central force. So this is about law of time periods. Now we see, just to our curiosity, what are the semi-major axis distances and time periods for some planets. Okay, if you can take the nearest planet as Mercury, so the semi-major axis, time period and the quotient, just we will see what are the sum values. For Mercury it is 5.79 and 0.24. This is 5.79 and 0.24. Okay, and what is the next nearest planet? We will take the Earth. So Earth, we know the time period is 1 year. We all know. So what is the semi-major axis? That is the distance from Sun to Earth. It is 15. We all know 15 means it is not 15. 15 into 10 to the power of 10 meters. That we all know that A is measured in the units 10 to the power of 10 meters. I already told you. So 5.79 into 10 to the power of 10 meters. So the most interesting planet and very far away from the sun next is Saturn. We are not discussing about all the planets, we will discuss some planets. So here the quotient, if you calculate and write the quotient by your own, you will get this nearly 3. Nearly means maybe 2.99 or 2.98 or 3.01, something like that, but nearly 3. The quotient will be constant in all, considering all the planets. Okay, what is the semi-major axis distance for Saturn? It is 143. It is 143 and it is 29.5 years, and the quotient will come to be same. Okay, and what is the farthest planet? The Neptune. For Neptune, it is 450 and 165 years. What is this? The farthest planet, Neptune, in our solar system. So this is all. This may also come to be nearly 3. So this is how we observe the planets, their distances from the sun and their time periods. So law of time periods is a very valid law, and the same was proven to be very right. So here we ended this session. We will come with some more interesting topics in the next video.